Hi. We're going to go over a couple quick calculations on calculating discrete probabilities. These are a couple examples that you've seen before. Revisit one at a time. So number 10 and 12 here have to do with a standard deck of playing cards. Oh, there you go. Standard deck of playing cards, number 10 and 12. So if you pick a card at random from a well-shuffled deck, just randomizing, what is the probability that you get a face card or a spade? So for a standard deck of playing cards, you need to know that the deck consists of 4 suits, 13 of each, 13 cards of each suit. So one of those suits are spades. So that means there's 13 spades at a total of 52 cards. Face cards are any cards with faces on them. So jacks, queens, and kings. And there are 4 of each. Jacks, queens, and kings. Okay. So in the standard deck of playing cards, if you had all of the playing cards in this box here, you want to find the probability of randomly selecting a spade. So I'm going to put all the spades in this one circle here. Or a face card. Now, I'm going to make another circle here, but I'm going to overlap them because there are 3 face cards that are also spades. So they fall in this little area right here. So if we were to count these individually, we would say, oh, well, there's 13 spades, right? 13 spades. And there's 4 of each face cards, and there's 3 of them. So 4 times 3 face cards. So we would say that's 12 total. And we would add these up, and we would get, okay, so there's must be 25 cards to choose from, or we can count as a success. Well, that technically is that's actually not true, because out of these 13 spades, 3 of them are face cards. So we need to subtract that 3, the jack of spades. The spade looks like an upside down heart, kind of sort of upside down fish, I guess. A heart multiple. Anyway, the jack of spades, the queen of spades, and the king of spades. So we have to subtract 3 of them to get 22 successes total. So to calculate the probability of two things that are not mutually exclusive, 2 things that can happen at the same time, you have to calculate the probability of the first one and add it to the probability of the second, and then subtract the probability of those 2 things happening at the same time. That's spade, and then union with the face. So we'll subtract the overlap. So the probability of pulling a spade would be 13 out of 52, plus the probability of pulling a face card is 12 out of 52, but then you subtract away the 3 out of 52, and that combines to be 22 out of 52. So formulaically, you would use this idea of when you're combining individual probabilities, or you can just count the fact that there's 13 spades, there's 12 face cards, but 3 less, that's 22, so 22 successes out of a total of 52 possible cards. So the answer number 10 would either be 22 out of 52 or the decimal equivalent of that. Okay, that's all you have to do. Number 12 is similar, but slightly different, because for number 12, the probability of drawing a face card or a 4, well, the face cards are again Jack, Queen, King, and then 4s, well, that's totally separate, right? 4s. And there are 4 of each of these in one of every suit. So there's 4 cards, 4 of each, so 16 total successes, so it's just 16 out of 50. There's no overlap between face cards and 4s. 16 out of 52. Or you could say, okay, what's the probability of drawing a face card? That's 12 out of 52. And then what's the probability of drawing a 4? Well, there's 4 4s out of 52. And then subtract the overlap. Well, there are 0 4s that are face cards. So it equals 16 out of 52. Either way you slice it there, it's 16 out of 52. You can leave that as a fraction too, or write the decimal equivalent. It doesn't matter. Number 11, you're given all the probabilities in table form. If one of the 1,156 people is randomly selected, find the probability that the person is a man or a heavy smoker. So we know the total is a 1,156. The total is 1,156. And we want the probability that the person is a man. So all the men are here. So 601 men. Or a heavy smoker. So heavy smokers were all different color here. All here. 88 total. So you might be thinking, okay, well, out of the 1,156 total, well, what's the probability that you would randomly select a man? That's 601 out of the 1,156. And then what's the probability of getting a heavy smoker? Well, that's 88 out of the 1,156. Should be a 6 here. 1,156. Sloppy. So then you would just add them up, right? Well, the problem with that is that there's this overlap. The fact that the 42 men are heavy smokers. So you do have to subtract the overlap. What's the probability that you're the man and a heavy smoker? Well, that's 49 out of 1,156. So the options to calculate the probability that a person is a man or a heavy smoker, just add the 601 plus the 88, and then divide that by the total of 1,156. So that would be 689 over 1,156, or that decimal equivalent of those two things. So if we did that, right, we would not be correct, because we're forgetting the fact that there's this overlap of 49. So we would have to subtract the 49 to get this. So 640 at 1156. So that's that, or the decimal equivalent is the actual answer. Now, alternatively, we could, since we have a table form up here, we could just say, okay, well, what's the probability of getting a man or a heavy smoker? Just add all of the numbers up that are inside. So inside the table really there's only these values here. Non-smokers, men, women. So we add the 431 plus 50 plus 71 plus 49 plus the 39. If you add up all those values, 431 plus 50 plus 71 plus 49 plus 39. Well, we should get, 431 plus 49. That's 430 plus 50. That's 480. 71 plus 39 is 70 plus 40. It's 110. So 0, 4, 640. Okay, you get that 640. So you can just count each piece once. That's the idea. So there's multiple approaches to a problem like this, where you have the information in a table form, the idea is that you don't double count the overlap. Okay, that's the big idea with calculating and interpreting discrete probabilities, especially if they're dependent or independent of one another.